Welcome to G Fun Facts Online. Today, we are going to dismantle a long-held cosmic myth and replace it with a reality that is far more chaotic, violent, and fascinating. For decades, the standard narrative of stellar death has been one of silence, followed by sudden catastrophe. In this traditional view, a massive star, a red supergiant, sits quietly in the dark vacuum of space. It burns through its final reserves of fuel, essentially holding its breath, until the core collapses in a fraction of a second. The resulting supernova explosion is the first warning the universe gets that a titan has fallen. It is a model of a silent countdown, followed by a blinding flash. But recent discoveries in radio astronomy have shattered this image. We are now learning that dying stars are not silent. They are screaming. Long before the final explosion, massive stars send out distress signals, complex, invisible signatures that reveal a tumultuous end-of-life crisis. These are not signals we can see with our eyes, nor are they the neutrinos that flee the core in its final milliseconds. They are radio whispers. These are faint, variable, and often delayed transmissions that tell the story of the star's final years. By tuning into these frequencies, astronomers are effectively building a time machine, allowing them to rewind the clock and watch the final, chaotic decade of a star's life after it has already died. To understand how we hear these whispers, we first have to understand why radio astronomy is fundamentally different from the optical astronomy most of us are familiar with. When we look at a supernova in visible light using a standard telescope, we are seeing the thermal glow of the exploding fireball. It is bright, it is fast, and it gives us immediate data about the explosion's energy and composition. However, radio waves tell a story of interaction. A supernova does not inherently emit strong radio waves on its own. The radio signal arises only when the rapidly expanding shock wave of the explosion slams into something. Specifically, it slams into the gas and dust that the star shed before it died. This is the key distinction. Dr. Yvette Sendez, a radio astronomer who specializes in these transient signals, describes the radio emission as essentially a crash report. The star sheds layers of itself years or centuries before the end. When the star finally blows up, the shock wave races outward and collides with those shed layers. That collision accelerates electrons to near the speed of light, spiraling them around magnetic fields and generating what is known as synchrotron radiation. This is what we detect as radio waves. This mechanism turns the surroundings of a supernova into a forensic scene. By measuring the brightness and timing of the radio signal, astronomers can calculate exactly how far away the gas was from the star. Since they know the speed of the shock wave, they can mathematically rewind the movie. If a radio signal peaks 1 year after the explosion, that might correspond to gas shed 10 years before the death. If the signal peaks 10 years later, it might reveal mass loss from a century ago. For the first time, this radio time machine is revealing that massive stars do not go gently into that good night. They undergo paroxysms of violence, shedding mass in eruptive burps and superflares that defy our standard stellar evolution models. This brings us to the mystery of the dirty fireball. For much of the 20th century, the standard model of stellar death assumed a clean environment. A red supergiant star would have a steady, gentle stellar wind, like a slow exhale, carrying material away at a constant rate. If this were true, the radio light curve of a supernova would be smooth and predictable, fading steadily over time. But the universe, as it turns out, is messy. In recent years, surveys like the Very Large Array Sky Survey and dedicated observations of unique events have revealed environments that are dirty, cluttered with dense shells of material sitting perilously close to the star. In early 2026, a team led by astronomers at the University of Virginia announced a breakthrough detection, the first comprehensive radio mapping of a type Ibn supernova. These are rare explosions that are hydrogen-poor but rich in helium, indicating the star had already stripped off its outer hydrogen envelope. The radio data revealed a startling history. In its final 5 years, the progenitor star had shed an enormous amount of mass, far more than a standard stellar wind could explain. This was not a gentle exhale, it was a violent purging. The star had ejected the equivalent of several Jupiters' worth of mass in a geological blink of an eye. This material formed a dense shroud around the star, waiting for the inevitable shockwave to light it up. So what causes a star to essentially vomit its outer layers just moments, cosmically speaking, before it dies? The leading suspect is not the dying star itself, but a hidden accomplice. Massive stars hate being single. An astrophysicist from the Harvard-Smithsonian Center for Astrophysics explains that over 70% of massive stars are born in binary systems. As the primary star swells into a red supergiant in its final phase, it doesn't just expand into empty space, it expands into the orbit of its companion. This interaction can be catastrophic. As the dying star swells, its gravity creates a common envelope scenario, or simply allows the companion star to gravitationally strip material away. The companion acts like a cosmic blender, churning the outer layers of the primary star and flinging them out into a dense spiraling disk or shell. A stunning example of this was the radio transient VT1210 plus 4956, discovered in archival VLA data. The signal was consistent with a supernova shockwave crashing into a shell of material ejected centuries earlier. The analysis suggested that a compact object, likely a black hole or neutron star, had plunged into the atmosphere of its companion star, spiraling inward and triggering a premature explosion. The radio signal was the scream of that merger, echoing through the centuries. While the crash report method helps us reconstruct the past, astronomers are desperate for a real-time warning system. Is there a radio signal we can detect before the star explodes? The answer might lie in masers. Maser stands for microwave amplification by stimulated emission of radiation. These are the radio wavelength cousins of lasers. They occur naturally in the dense, dusty envelopes of red supergiant stars. Water molecules and silicon monoxide molecules in these clouds can be pumped by the star's radiation, causing them to emit coherent, incredibly bright beams of radio light. For decades, we have used these masers to measure the distance to stars. But recently, researchers have noticed that masers can flare. In the chaotic final stages of a star's life, as it begins to pulsate violently or interact with a binary partner, the shockwaves traveling through its atmosphere can trigger sudden, intense maser flares. A superflare in a water maser could theoretically serve as a pre-supernova alarm. If a red supergiant like Betelgeuse were to suddenly exhibit a massive spike in its water maser emission, it could indicate a destabilization of its outer envelope, a potential precursor to core collapse. While we haven't yet definitively linked a specific maser flare to an immediate subsequent supernova, the physics suggests the connection is there, waiting to be found. It is also important to note that not all dying stars produce these radio whispers. Type 1 supernovae, the standard candles used to measure the expansion of the universe, are famously radio quiet. They occur when a white dwarf star explodes. For years, the lack of radio emission from Type 1a events was taken as evidence that they explode in clean environments, supporting the theory that they are caused by the merger of two white dwarfs, which would have no gaseous atmosphere. However, the discovery of SN 2020 EYJ changed the game. It was a Type 1a supernova, accompanied by a helium-rich radio signal. This whisper confirmed that at least some Type 1a supernova come from a white dwarf stealing matter from a helium star companion, creating a messy, radio-bright circumstellar environment. The silence of Type 1a supernovae is not absolute. We just weren't listening hard enough. Looking ahead, we are currently standing on the precipice of a golden age in radio astronomy. The instruments of the past were often too insensitive to hear the faintest whispers of dying stars, picking up only the loudest shouts of nearby or particularly dense interactions. The coming Square Kilometre Array, or SKA, a transcontinental radio telescope being built in Australia and South Africa, will change everything. With sensitivity hundreds of times greater than current telescopes, the SKA will be able to detect the radio signatures of normal supernovae in distant galaxies, not just the rare, radio-bright oddballs. More excitingly, the SKA, along with the Vera C. Rubin Observatory's optical survey, will allow us to correlate radio transients with optical precursors. We might soon detect a radio flare from a massive star's pre-supernova eruption in real time, alerting us months or years before the star actually explodes. Imagine a galactic weather forecast that predicts supernovae. Attention observers, a red supergiant in galaxy M51 has just emitted a terawatt radio burst and a maser flare. Core collapse is estimated within 3 to 5 years. The phrase, "whispers before the bang," is a poetic contradiction. In the vacuum of space, there is no sound. But in the electromagnetic spectrum, the universe is a cacophony. For centuries, we have been watching the fireworks show of the cosmos with our ears covered. Now, with the advent of time-domain radio astronomy, we are finally uncovering the ears. What we are hearing is a story of complexity. Stars do not simply run out of fuel and turn off. They fight against their own gravity. They interact with their neighbors. They belch clouds of dust and gas. They scream in maser light. The radio signatures of dying stars remind us that creation and destruction are messy, entangled processes. The next time you look up at Betelgeuse, the bright red shoulder of Orion, remember that it is not just a point of light. It is a boiling, churning cauldron of plasma, likely surrounded by invisible shells of its own past, whispering secrets to radio telescopes that we are only just beginning to understand. We are listening now, and the silence has never been louder. Thanks for listening to G Fun Facts Online.